In this video, we'll continue looking at complex numbers, and we started with some basics of what complex numbers are, some adding, subtracting, multiplying, and even dividing. And let's move on to simplifying square roots of negative numbers so that we can rewrite those as imaginary numbers. Just what you'll need to recall is how to simplify a radical. So if I just had a 49, I could see that as a 7 times a 7. So I'm multiplying 2 7s to get a 49. Whenever you get a pair of numbers in a square root, you can remove them. So this pair comes out of the radical as a positive 7. Now it could be that you've already remembered this, you may already know that, so you could skip through, maybe go a little faster with the video, but in the case you need a review on simplifying radicals, that's what it would look like. So that's a simpler example. Let's look at our example, the square root of negative 49. That's going to be the square root of negative 1 times the square root of 7 times 7. Whenever I get a pair, so I'm looking for what number is going to multiply by itself to get a 49, and the answer is 7. So this is an I times 7. And proper format, we're going to put the 7 first. Remember when we had a radical like the square root of 3 times I, we wrote it as I times the square root of 3. But otherwise, we'd always put the coefficient, the 7, first. This 108 is a little bit different because 108 is not a perfect square. But I'm going to do, off to the side here, I'm going to take that 108 and do what's called a prime factorization for 108. I'm going to look for what numbers go into 108 evenly. I know right off the bat that a 2 will go in because it's even, and if I do 108 divided by 2, I'd get 54. Do you remember this? So 2's prime, so I circle it. 54, I'm looking for two numbers that multiply to get 54. 9 is, I could do a 2 again, but I'm going to jump to the chase here and say, 9, 54 divided by 9 is 6. And then the 9 is a 3 times 3. 6 is 2 times 3. That's called a factor tree. And I can use that factor tree to rewrite this. I'm going to be really careful with that negative, not to lose it. But 108 we could rewrite from our factor tree with 3 2's. I know you could write it 2 cubed, but I'm going to write it 3 cubed. Oh, actually, you know, I'm reading that wrong. It looks like there were only 2. Good reason to write more clearly. With this pen, it's sometimes it's a little fat, and I can't see it fully, but it looks like there were 2 2's, right? And then there were 3 3's. And what I'm looking for is pairs. So when I see a pair of 2's, that could remove from the radical. Let me catch us up here. I'm going to go ahead and I'm going to start with that 2. So 2 2's can be removed and we get a 2. 2 3's remove, and then what's left? What's left inside our radical? We still have our radical 3, square root of 3, and then we have our I. Again, a little bit better way to write that is going to be to put this I up in front. So it would look like this. 2 times 3 is 6. So I'd say 6I times the square root of 3, just moving that I in front of the radical. And that's how I could simplify the square root of negative 108. Let's look at another example. This one gets even more complicated. but we can handle it. And so 4C, when I simplify that, be careful of that subtraction, because according to the order of operations, I'm going to do any exponent first. So that's the 9. And then I'm going to multiply before I subtract. So I've got to think of this 4 times 2 times 5 as being grouped together before I subtract, right? So be careful of that. I'm going to do that mentally, because 2 times 5 is 10, and 10 times 4 is 40. So I'd have the square root of 9 minus 40. If I do 9 minus 40, I'd get negative 31. Square root of 31. 31 does not have any perfect squares in it. So all I need to do is pull out that negative 1, the square root of negative 1 is I, and then we still have that 31 in the radical. So it would look like that. I times the square root of 31. Are you ready for something, a step up? We could perform some operations on these numbers. So now we're going to simplify the radical and then combine them. When I do the square root of negative 64, you might recognize that 64 is a perfect square. 8 times 8 is 64. And then square root of negative 1 is I. And I'm going to subtract. Square root of 25 is 5i. So 8i minus 5i. 8 minus 5 is 3. So you guessed it, 3i. Are you familiar with 5b, this negative 3 minus the square root of negative 7 squared? Do you see how I could start by changing that to a minus 7i, so negative 3 minus 7i. But when I square that, it's the same thing as multiplying it by itself. So negative 3 minus square root of, oh, I dropped the square root, sorry about that. Square root of 7i times negative 3 minus the square root of 7i. But this a plus b squared, what that means is a plus b times a plus b, right? So I'm expanding it. When I do the FOIL, negative 3 times negative 3 is positive 9. Negative 3 times negative square root of 7i would be plus 3 square root of 7 times I. Be careful not to blend those together. And then outside times outside, negative 3 times negative square root of 7i would be another plus 3 times the square root of 7i. And then last times last, negative square root of 7i times negative square root of 7i would be positive square root of 7 times the square root of 7 is going to be 7, isn't it? And then I squared is going to be negative 1. So it's going to be negative 7. Combining like terms, I'd have the 9 minus 7 is 2. And then 3 square root of 7i twice would be double. So 3 square root of 7 plus 3, let me write it just in case. When I have that twice, it's going to be doubled. So plus 6, so 3 plus 3. You don't double the square root of 7, do you? Because it's like 3x plus 3x would be 6x, not 6x squared, right? In the same way, 3 times the square root of 7 plus 3 times the square root of 7 would be 6 times the square root of 7. Last step is I'm going to rewrite this to put that I in front of the radical. So it looks like I'd get 2 plus 6I times the square root of 7. Are you ready to try just a couple more things? This is the last topic, I promise. Simplifying a power of I. We could see this example over here, I to the 65th power. Do you see what they did? They did 65 divided by 4. 4 goes into 65 16 times with a remainder of 1. You could do that on your calculator. Try it. 4 times 16 plus 1, you'd get 65. So what that tells me is I could take those 65 i's and break them up into 16 I to the fourths, and then I'd have 1 I left over. Well, I to the fourth, I to the fourth is just going to be 1. Let's look at y. When we had I squared, do you remember that was, I squared was negative, or I'm sorry, let me back up. I is the square root of negative 1. Let me actually call I already wrote this out, so let me call your attention over here to the right. I, by definition, is the square root of negative 1, so just I. If I squared that, if I square negative 1 square rooted, I'd just get the negative 1 back. Now, if I did that cubed, then I'd have an I squared times an I, so I'd have a negative 1 times I, or the opposite of I. Now, what happens with an I4 is I'm going to go back to this I squared. I squared was negative 1, so I'm going to get a negative 1 times a negative 1 is equivalent to 1. Now, if you didn't understand that, think of this as a circle and think of it like sometimes we refer to this type of problem as clock arithmetic. You know, if you went around the clock and you got back again, you'd just repeat to 12 again, right? And now we're going to start 1, 2, 3, 4, 5, 6, 7, up to 12, and then we restart. You keep restarting. So when I move around a circle, so I'm starting with I to the 1, just I, and then I have I squared is negative 1, I cubed, negative I to the fourth, 1. Well, when I keep going to I to the fifth, so 1, 2, 3, 4, now I to the fifth, it's the same as I, because that I to the 4 just simplified as a 1. So this I to the fourth is 1. Doesn't matter how many times you multiplied 1 by itself. 1 times 1 times 1 times 1, 16 times was still just 1. So watch what would happen if I did this I to the 65. I'd go 4, 8, 12, 16 times around, and that would get me to 64. And then one more would give me one more I. So I'd end up here on I. So that's what they're doing here. I hope that makes a little bit of sense. If you need a little more help with that one, let me know, and we could go over it even a little bit more detail. But that would be 1 times I, or just I. But with the example we're going to do that hasn't been done yet, I to the 31, if you think of this clock arithmetic again, if we started at I and we go around 1, 2, 3, 4, keep going, I could get up to 28, 29, 30, 31. Do you see where I'd land? I'd land Oh, I don't think I counted that right. I'm sorry. Would you excuse, let me back up and do that one more time. I think I started the wrong place. Okay, let's try it one more time. Well, we're gonna start here at I and go 1, I to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 25, 26, 27, 28, 29, 30, 31. Do you see where I'm landing at I cubed? Let's see how that could work out with division. How many times would I go around? Well, that's going to be the 7. And it doesn't even matter that it's 7 times, right? It didn't matter how many times I went around and around. All that mattered was, where did I land? The remainder is 3. So what does that tell me? That when I go all the way around, I'm going to get to that I to the 4 7 times. So from starting at I'd get there to the I4 7 times. But then I've got 3 more to go. 1, 2, 3, and where do I land? I land at I cubed. So I could rewrite this. So maybe this is what will make more sense to some students. I could write I to the 31 as, I'm looking at getting rid of any power of 4. So I could get 7 powers of 4. 4 times 7 is 28. So there's 28 of the 31. And what is that? It's just a 1 to the 7th power, which is just a 1, right? And then I'd have 3 left over, because 31 is equal to 4 times 7 plus 3 left over. I cubed is the negative I. So it looks like this 6a is going to be I to the 31 would be an I. So we could write that as negative I. I to the 31 equals negative I. Let's look at, or actually that's it. I'm sorry, we have nothing else to look at for this section. But if you do have questions and you're in my class, I hope you'll reach out to me. I know that these videos could get pretty long. I try to keep them in 25-minute or less sections. That's why this one broke into 2. You may get to some of the topics that were easy for you that you already knew. Some of it is review from beginning algebra or intermediate algebra or pre-algebra even. So maybe you could fast forward through those parts of the video in the future. But I do hope that this video was helpful. Please let me know in class if you had any questions. And thanks for making time to watch your videos.